بسم الله الرحمن الرحيم. هنقول في الجزء الثالث على البابليك كي كريبتو سيستم بعض الملاحظات عليه. احنا ما قلناش كل حاجه طبعا، هي الفيديوهات ديت عباره عن ملاحظات وليست محاضرات كامله على الموضوع. عندنا ريفرنس تكست بوك والمحاضرات بتاعه الكريبتوغرافي بتاع البروفيسور بار متخصص طبعا، فيها تفاصيل اكتر، واحنا هنا بنعمل ملاحظات سريعه و some tutorial session، يعني هنحل بحل معاكم بعض الاكزامبلز علشان اشجعكم تحلوا بايديكم، وبكتب البراهين الرياضيه كامله، مع ان بروفيسور بار بتوع الكمبيوتر ساينس مش بيهتموا بالماثيماتيكال بروف، لكن احنا دوت المين انترست بتاع الكورس بتاعنا. ففي بعض الملاحظات الرياضيه التانية لازم برضو نقولها، وهي ليه الفاي of n kept secret؟ why phi n is kept secret؟ بعد دي الملاحظة الأولى. طبعا في إجابة سهلة، إنه إحنا نقدر نكتشف الانفرس كي أو السكريت كي the inverse of e لو عرفنا الفاي n. ليه؟ because دي the secret key، طبعا secret ديت الكلمة الانفورمال، لكن هي the private key. can be computed solving the linear congruence E x congruent 1 mod phi n. دي طبعا دي العلاقة اللي بتحدد لي ازاي نحسب الدي. فطبعا لو كنا عارفين الفاي n، this congruence can be solved very easily as we know from number theory, and we have done it many times using Euclid algorithm. دوت إجابة السؤال طبعا بكل بساطة، إن إحنا نقدر نجيب الدي is e bar the inverse the value of x of this equation أو congruence طبعا. السؤال الثاني فيه هو هل لو عرفنا الفاي ان نقدر نكتشف مين هم التو برايم نمبرز؟ نمبر 2، this statement to be proven if phi n is known, then p and q are easily found by some mathematical relations to be proved soon. Direct mathematical relations. Why is that? This means that n can be factored. If we know phi n and n with the conditions of the RSA, that is n is a product of two different primes, if we know phi n, then we can find p and q easily. Why is that? Proof. The proof is, remember that n equals pq, product of two primes, p and q are different primes. Therefore, applying the Euler-Tauschent function, therefore in phi n, as you know, phi pq, and using the multiplicativity of phi is multiplicative, gives Multiplicative function means if the two numbers multiplied as an argument here inside the function are relatively prime, so we can distribute the function value in the usual manner, phi p times phi q. And we know that p is prime and q is prime, and the value of the Euler function at prime numbers is known to be p minus 1 times q minus 1. Why is that? We proved this in the first session of revision about the number theoretic terms needed for understanding the RSA. Why is that? It's easy, because all the integers from 1 up to p minus 1, the number exactly preceding p, they are all relatively prime to p, because p is a prime number. Therefore, let's multiply this. Distribution will yield pq minus p, then minus q plus 1. Some more. pq, remember, this is the n. And here we can put this in this form. Therefore, this is phi n. So now we have pq equals, simple algebra gives p plus q, their sum equals n minus phi n plus 1. This is second equation we have. This is the first equation we have. So if we know phi n, we know exactly what, of course, n is known to the public because it's part of the general or the public key. So now we have the value of the product of the two numbers p and q and their sum. So we are in a position to ask a question, can be solved by a 9th grade student. If you know the product and the sum of two numbers, how can you find these two numbers? So revise the question again. If phi n is known, then p and q are easily found by some mathematical relation. Or in other words, n, or to say n can be factored. So the knowledge of phi n implies the knowledge of p and q. That's to say, then it implies the factoring of n. For this, and there is no way to evaluate the value of Euler function except for using the factorization techniques. And our methods depends on the difficulty of the factorization into prime numbers. Of course, for the big primes, at least 100-digit numbers, as our textbook from the 2000 says. So now let's think about this question again. If you know the product of two numbers and their sum, how can you find these two numbers explicitly? Okay. If we know the difference between them, we can add and subtract the two equations. But what is the relation between the subtraction or the difference between two numbers and their product and their sum? This is a known identity. We use the identities a minus b all squared equals a square minus 2ab plus b square. And therefore, a minus b is root of this. We wait for a second, some few steps. We can change this into the form plus 2ab plus b square. This, why is this? Because this is a perfect square trinomial, which factorization yields a plus b. Or what we have done, we changed this negative into positive. So we added 4ab. So we have to subtract 4ab. This is the same as this. but this will be of the form a plus b all square minus 4ab. Therefore, we can write a minus b in the form square root of this. So the difference between two numbers, this is a simple algebraic identity. Of course, this is if a is the bigger one than b, so we take the positive square root. So a plus b square minus 4ab. Therefore, this is identity. It is immaterial with the p and pq and our situation here in RSA. This is for any two numbers. The difference between two numbers can be found using their sum. This is the difference. This is the sum. This is the product. So we can use this relation here. This is the identity I mentioned. Therefore, using this identity for our p and q, we get p minus q is equal to root p plus q square minus 4pq. And in our setting, the p plus q is this form. N, so p plus q is n minus phi n plus 1, all of this to be squared, minus 4, the pq in our notations is the number n. So if we know n and phi n, one can easily find p minus q. This is relation 3. And using 3 and 2, one can conclude easily we have the sum and the difference of two numbers. This can give you p and q. Adding these two equations, p plus q and p minus q, if you add them, you get 2p. If you subtract them, you get 2q. So equation 2 plus equation 3 gives p equals, or 2p equal, to give p equal the sum of these two values, plus 1 plus this big square root to be written here, n minus phi n plus 1 all squared minus 4n. This is the value of q, this is the value of p, and this will be similar value of q. The same thing, but we subtract 2 plus minus 3. Their sum will yield p and their difference will yield q in the same manner. This is the same and this radical is the same. These are the two values of p and q. So by this we discovered the factorization of n into the two prime numbers comprising this number n. So for this, once more, if we know n and phi n, where n is a product of two numbers p and q, one can factor n easily by this very simple techniques of elementary algebra. So it is said that knowing phi n is not easier than factoring n. Because if we know phi n, we can find p and q. If we know p and q, we can find phi n. And no easy method or no method of calculating the Euler phi function is known without the use of the prime factorization. Okay, we have some exercise about this form. Exercise 1. He asks you to find the primes p and q. Find p and q if n equals pq and n is this number, where n is 1, 4, 6, 4, 7, and phi n is 14400. In fact, this is a very small number. Even a small pocket calculator can recover the 2 primes comprising this number. So I'll show you 14647. Use the factor key. So you find that n equals 97 times 151. These are the P's and Q. If you call the bigger prime of them P, so this is P and this is Q. Why we are given phi? Because the question asks you to find P and Q not by the calculator but using this formula. So how to ensure that you use this formula, I can ask you to give a proof that n can be factored if you know phi n. This is a mathematical part. But what about phi n? We can, if this is allowed, if you are allowed to use the calculator or the tables of prime factorization, I ask you to verify that phi n is correct. So we change the question into a verification question. Or change the number for a little bit bigger than that, with the calculator will not be able to factor it into its prime factorization, because this is a small little pocket calculator which has a small memory. Verify phi n. So let's verify phi n. Phi n equals phi of 97 times 151, which is phi 97 times phi 151. Again, the basic properties of Euler phi function gives you 96 times 150. So 96 times 150 will give you yes, right, which verifies the given data. The other solution is to use this formula.